Welcome to Maths with EJD. In this video, I'll be talking about resource constraint project scheduling with linear programming. We have a kind of project situation like this. Consider a construction project with the following tasks. The following tasks. Okay. Imagine that task A, the duration is 2 days. Then workers required. You need 2 workers for that. Task B, the duration is 3 days. 3 workers are also required. 3 workers required. And then task C, the duration is 1 day. And number of workers required is also 1. Okay. Now the company has a total of 4 workers available. And tasks can actually overlap. Tasks can overlap provided the total worker usage does not exceed the limits. So that's the situation we have. So how do we formulate this? So linear programming formulation of this now will be something like this. So first of all, we have our decision variables SA, SB, SC, which are the start times for tasks ABC. Okay. Then we have R A comma T, R A comma T, RB comma T, and RC comma T, RC comma T. And these are binary variables. They are binary variables indicating whether each task is active at time t. Okay. Now, those are the decision variables, right? Like we said, I can indicate this. These are decision variables. So then we talk about the objective function. Objective function. So the objective function is to minimize the total project duration. Okay. So we just minimize the maximum of start time of A plus the 2 days A takes, then start time of B plus the 3 days that takes, plus start time of C plus the 1 day that should take. That is what we want to minimize. Or equivalently, we can say minimize where D is the project duration. That's another thing. So we can do that too. And then we talk about the constraints. So we have the constraints. So first we have the resource limits. Resource limit at any time t. So that will be 2 RA, comma t plus 3 RB, comma T. You know, the workers are the resources here now. So then one RC, comma T. And all of that should be less than or equal to 4. So we're actually minimizing, we actually, this is actually a constraint on the number of workers. So then we also have a constraint on task duration. Task duration, we have a constraint on that. And that is for each task, ensure the task is executed for its entire duration. For example, for task A now, we have um we have summation of T equals SA up to SA plus 1 of all the RAT, that should be equal to 2. And then, of course, we have the same for, because it takes 2 days, right? So that's one constraint. We also have, so it means we also have summation T equals SB from up to SB, um, uh, that A, where is it coming from? A takes 2 days. So all this now up to, before, by the same token, so we say SB plus 1, that's RB, comma T, and all of that should be equal to, that's 2, 3, right? All of that should be equal to 3, talking about duration, whatever happens. So summation of T equals SC from up to SC plus 1, RC, comma T, all of that should be equal to 1. Okay. Then we also have task dependencies. So we have task dependencies. So here, for task dependencies, now that talks about if one task depends on the other, task dependencies. So if one task depends on the other, so in that case, we will have SA plus 2 is less than or equal to SB, right? So in that case now, we have, so that's the formulation of the problem as we have it. So that's the formulation of the problem. We can have some sample solutions. Using LP solvers such as Python Pulp or Gurobi, we can solve the problem to determine the start times and active periods for each task while ensuring that constraints are satisfied. So we can have the optimal schedule, like task A will start at day 0, ends at day 2. Task B starts at day 2, ends at day 5. Task C starts at day 5 and ends at day 6. So that's like we are going a total of 6 days in that regard. I mean, so we can actually solve this using Python, especially Pulp, because we have this um two-dimensional, we have these binary variables, RA, RB, and RC. I think it's important to note that linprog doesn't do very well with this. So because of that, I've only used Pulp here. So I tried linprog too, but I discovered Pulp is, in fact, from our experience, Pulp is more suited for most of these linear programming things. So you just you define the variable, the tasks, and with their duration and the number of workers, the total workers you have, the time horizon. That's like maximum project duration, for instance. Like that, if you add up 2, 3, 1. I mean, that's just like an upward projection, right? Then you have decision variables, start times, end times, and whether the project is active or not. So, and all of this just goes. And I mean, we want to take some time to really look at the code, but then I'll just run this, right. And so we have that total project duration is 6 days, just like what we projected already, right? So task A starts at 0, ends at 2.0. Task B starts at 0 and ends at 3.0. Task C starts at 0 and ends at 1.0. So in that case now, that's what we have. So we can come back here and say Now, strictly pulp, because limprog doesn't give a very good answer in this case. So we say using um, using pulp in Python. I guess I want to change that. Using pulp in Python, we get we get you know, the variables we have, right? SA, the start time for task A is actually day 0, right? And it ends at day 2. So that SB actually starts at day 2, day 2.0. So the start time for task 2 is day 2 and it ends on day 5. And SC, the start time for task C is 5.0. And because it takes 1 day, right? We now have total duration. Total duration is actually SC plus the 1 day it will actually require to do that. Okay, this now. So that's what we want to really minimize. So then we have 5.0 plus 1.0. So and that is 6.0. So the project takes a total of 6.0 days. Now the solution looks very straightforward, but um if things get really complicated, at least we have a framework to answer this. So some practical applications for this would be things like construction project planning, IT project management, manufacturing and production scheduling, event organization with resource constraints, even software projects, software design and things like that can also fit into this. So that's the end of this video. um it's been a very sweet ride. In the last video, I'll just talk about how far linear programming can go, because it has its own limitations. Some problems are in non-linear form, and maybe in sometime in the future I may make a series of videos on quadratic programming or something like that, non-linear programming in short. So watch out for that. Also, if you have not subscribed to this channel, be sure to do that right away. Hit the notification bell also, so you can always get notified each time a new video is released. Then don't forget to comment. Let me know if you want to teach a topic or solve a problem, and like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Bye.